In this video, we are going to look at earthquakes, and specifically we're going to look at how to triangulate the epicenter of an earthquake and how to use Mercalli scale data. So there's also Richter scale data that we're all more familiar with, like a 6.0 earthquake or a 3.3 earthquake. But in this video, we're going to focus on the Mercalli scale because it's something we're not as familiar with. But starting first with triangulation of an epicenter. So we need to have seismographs, which are instruments that measure and record earthquake waves, and we have to have those waves in what's known as a seismogram plot. So you can see we have three different locations. We have Chicago, Rio de Janeiro, and Cork in Ireland, and we have earthquake waves, specifically body waves, present on these seismogram plots. So the first wave to arrive at a seismic station is a P wave, because it travels the fastest through the Earth. The next wave that arrives is an S wave. And what we are interested in for each of these stations is the arrival time of the P waves and S waves. So I'm going to highlight when the P waves arrive for each of these with yellow, and then I'm going to highlight the S waves with pink so that we have two distinguished different colors. So go ahead and get those in. And what we're going to do is we're going to look at the plot, and we see that along the bottom axis we have time. So we're going to look at the way the graph is plotted and then figure out the time of arrival for each P and S wave. So for the P wave in Chicago, we are looking at it arriving at 6.2 minutes. So I'm going to make note of that up here. Each of the faint lines is 0.2 minutes. It's one faint line past 6, so 6.2. We look at the S wave for Chicago, and we have 11.2 minutes. Again, going down to the horizontal axis to see we're one faint line past 11. So I'm going to calculate, or visually estimate, the arrival times for the P and S waves in the other locations, and then hold it up for you. You should be doing the same in your packet. And once we have these, so I've gone through and visually estimated. Chicago, we have the P wave at 6.2 minutes, the S wave at 11.2 minutes. Rio de Janeiro, we have the P wave at 9.4 minutes, the S wave at 17.1 minutes. And in Cork, we have the P wave at 11.1 minutes and the S wave at 20.9 minutes. What is the most important thing is what the title of this sheet is, S minus P times. So we have to take the S wave time and subtract the P wave time, and I'm going to write that in the middle between them. So 11.2 minus 6.2 for Chicago gives us an S minus P of 5.0, subtracting those two out. For Rio de Janeiro, we have S minus P, and we have 17.1 minus 9.4 is going to give us an S minus P of 7.7 for that one. And then for Cork, we are having an S minus P of 20.9 minus 11.1, 8 is 9.8. Is that right? Yes. 9.8 minutes. So we have now calculated our S minus P time interval for each of the three stations. The next thing we're going to do, we're going to keep this where we can easily access it because we're going to need it again, is we are going to go to a travel time curve. So in your figure, you might have really small dots. You want to connect those dots to make the S wave travel curve and the P wave travel curve. The great thing about this graph is it allows us to take travel time, like an S minus P time interval, and convert that to a physical distance in terms of distance to the epicenter from the seismic station that we're investigating. So what we're going to do is we will start with Chicago. In Chicago, we have a 5-minute S minus P time. So I'm going to make note of that. Chicago has an S minus P time of 5 minutes. So the first thing we want to do is we want to take a ruler and measure what is 5 minutes on the vertical axis. So I take my ruler, I measure 5 minutes, and I find that it is 2 centimeters. Now, what we're going to do, I got to hold this up so I can actually do it, is we are going to be taking our ruler and we're going to be looking for where there are 2 centimeters between the P and the S wave. So you can see here it's more than 2, so I slide it. And you want to keep it straight up and down. You don't want to have the ruler tilted at all because that's going to screw up our measurement. Until you can get to exactly where there are 2 centimeters between the S wave and P wave. So when I do it sitting down, it's easier if you put the 0 on the S wave. You keep the ruler straight up and down and you slide it until the P wave hits where you're interested in, which for us again is 2 centimeters. What I'm going to do is I'm going to use the ruler to go down to the horizontal axis, which I'll hold up for you in just a second. There are 2 centimeters between the P and the S wave with my ruler. I go down to the horizontal axis and I make a tick mark. Or the other way you can do it is you can take your pen or pencil and you can draw a line all the way down. So again, this is where there were 2 centimeters between the P and the S wave. I draw the line all the way down to the horizontal axis, and we can see that Chicago is 3,300 kilometers away from the epicenter. So I'm going to write that down as a note. We then need to do the 2 other stations, so I'm going to take notes on their S minus P time. So Rio had an S minus P of 7.7 minutes, and Cork had an S minus P of 9.8 minutes. So we're going to do the same steps. For Rio, we're going to measure 7.7 minutes on the vertical axis, then find where there's that same amount of centimeters between the S and P wave vertically. So go ahead and do that. 7.7 minutes. Again, your numbers might be a little bit different with the centimeters because your figure is a slightly different size. But 7.7 minutes, I'm getting about 3.2 centimeters, so I slide the ruler until we get to 3.2 centimeters, and then I'm going to draw the line straight down. So for me, I'm finding that Rio de Janeiro is 6,500 kilometers away from the epicenter. So make note of that. And then Cork, 9.8 minutes, is about 4 centimeters. And there are 4 centimeters and about here. And so we're looking at 8,400 kilometers. So again, for each station you do the same thing. You measure the S minus P time on the vertical axis. You then slide your ruler till there's that same distance. So for Chicago it was 2 centimeters. So there's 2 centimeters here. Go down, find the distance to the epicenter. Next we have a map, and I've already put the location of each epicenter on the map. Sometimes you'll be given coordinates and you will have to place the stations before you do the next step. But what we're looking at is now we are ready to use a compass to draw circles to figure out where all 3 circles intersect. That is our epicenter. So the first thing with the compass is you can see that the metal point and the pencil are not level. They're not even. So what we want to do is correct that, because a compass is going to work much better and accurately when we correct that. So you pop the tab, you set the compass on a nice flat surface till both the pencil and the metal tip are touching it, and then you reset the pencil. So now you can see our pencil and metal tip are nice and level with each other. And what we have is, let's first start with Chicago. Our distance is 3,300 kilometers. So what we are going to do is we are going to take our compass and spread the legs of it until the 2 tips are 3,300 kilometers apart on the scale. I'm going to do that down here. It's a little bit easier, holding it down instead of up. So 3,300 kilometers. Our compass is now set. Make sure you go to the correct station. For us it's Chicago, which hopefully, since we're from around here, everybody knows where that is. And then once you have it, your legs set, you make a circle with your compass. And this compass is not working out so great. My pencil shifted, that would be part of the problem. There we go. So now we have our circle, and I'm going to go over it in marker because the pencil is going to be really hard to see on the screen. At least where it showed up on here, I can go over it. And so it's not a perfect circle because I went over it by hand. But what we know as of right now is that the epicenter is somewhere on that circle. So we take our second station, Rio de Janeiro, a distance of 6,500 kilometers, and we do the same thing. Set our compass to 6,500 kilometers, which is about there. And then we draw our circle. And this time we don't need to draw the whole circle. We just need to draw the portion of the circle where it intersects with our Chicago circle. So we have that. And what we know now is that the epicenter is either located over here or somewhere over here, because we have the 2 intersections of these circles. To figure out which one it is, we're going to take our last circle, which is Cork, Ireland, and we know that the distance for it is 8,400 kilometers. So we set our compass to 8,400 kilometers, which is about there, and we go ahead and draw the portion of the circle around the Cork, Ireland that intersects with our other 2. And where all 3 parts of our circle intersect, we have our epicenter. And we could give latitude, longitude coordinates for it. We could look at plate tectonic boundaries and see what likely caused this earthquake. But we have pinpointed the epicenter of an earthquake using the travel time curve for earthquake waves and seismic data from an actual earthquake. The last thing that we are going to look at in this instructional video is using Mercalli scale data. So Mercalli scale is a way of not necessarily measuring an earthquake or quantifying, but describing an earthquake. So when an earthquake happens, you can go onto the USGS website, and they have a link where you can submit a response to an earthquake using a Mercalli scale. So if you're in the earthquake, you can use this scale to describe what you experienced. You'll see that on the low end of the scale, say a number 1, the earthquake is not really felt except by very few people in very favorable conditions. You move up to a number 2, it's felt by people at rest, so people laying in bed notice something is happening, and typically in high buildings, because high buildings, the height of the building actually increases the amount of shaking felt as the building enhances those waves. A number 3, most people recognize as an earthquake. They're aware that it's not just a truck passing by in the street or a train, that it is actually something quite larger. A number 4 feels like a heavy truck striking a building, so you definitely feel a jolt. You might hear the building make a loud pop noise as parts of it resettle or get shifted. At number 5, loose items are knocked over, and there is some breaking of the items, maybe a vase, glasses, dishes, whatever it is. A number 6 has furniture moved, so heavy furniture might be moved across the room. There is slight structural damage, and you can read that it gets more and more intense all the way up to number 12, which is essentially total destruction. Objects were actually thrown into the air. So when we look at damage in a Mercalli number 12, we'll see damaged cars, and they will often be flipped over onto the hood of the car or the top of the car. And a lot of people think the car was rolled over, which is not the case. What happens, if you look at the car closely, there's no damage on the sides of the cars. If it were to be rolled over, there would be damage on at least one side of the car. What happens with the waves, you can actually see the ground and the waves coming through the ground. They're so intense. The cars are actually popped airborne, and because the wave is rolling, they actually flip over in the air and land onto their top. So what can we do with Mercalli scale data? The idea is that thousands of people reply with what they experienced in the earthquake. In different locations, we can give the average Mercalli number to what people experienced, and then we can contour these numbers. So we draw a contour around all the number 12s, a contour around all the number 11s, the number 10s, the number 9s, and so forth. And so in your map, you should be drawing contour lines similar to what I'm doing. We have a number 12 in the center, then 11s, 10s, 9s, and so forth. We'll keep drawing the lines here. And we're not drawing a line through the numbers like we did for topography. We're drawing a line around the numbers, so it's a distinct difference. We have the number 6, kind of like this. We have our number 5. I'm drawing, so I have half of it drawn now. We can see the center of intense shaking, and it's getting less and less amount of shaking and damage as we move out. And this could be from what people replied to a survey with, or surveying the destruction and damage after the earthquake. And then I'll draw this one. So what we see is that we have very intense shaking experienced and total destruction in this location, and then people are saying, or damage is demonstrating, there was less and less shaking as we move away from there until we get over here. And again, we have very intense shaking, lots and lots of damage. And so say this was only one earthquake. The question becomes, how can you have what appears to be two different epicenters? That is not the case. You will only have one epicenter for an earthquake, so something else is going on in this situation, the geology of which is playing a very significant role. and which we will discuss and determine in detail in the lab that we do this week. So, for this video, we have looked at triangulating the epicenter of an earthquake given real-world data, and also at looking at applying Mercalli intensity scale data, which you will have to do in the lab in a physical geology course.